Welcome viewers. In this video, we are going to discuss about classification of loads. This is stage 3 of 7 for 220 kV transmission line double circuit tower structure loadings using Indian standard IS 802. So before going to watch this video, we request you to watch our previous video of stage 1 and 2, which is talking about the wind load calculation and the general input required for 220 kV transmission line tower for Indian standard IS 802. So these are the three classification or requirement of structural loadings for transmission line towers. So this is common and applicable for all the voltage level and all the type of either it is a single or double circuit or multi-circuit transmission line. So these are the three major classifications of structural loadings which are applicable for all the type of transmission line tower. So first one is reliability requirements or climatic loads. So there are various climatic loads such as wind, temperature, snow, which you can see the pictures on that. So these are the climatic loads which can be applied on the entire components of a transmission line. Say for example, a transmission line tower structure, insulator, strings, accessories, hardwares, earth wire. So all those components of transmission line towers are subject to the climatic loads of wind, temperature and snow. So these all load combinations and load parameters are comes under reliability requirements. Second one is security requirements. So this is a failure contaminant loads, because the transmission line tower used to run over various locations. In this, there might be, due to the material quality, the poor quality, there may be a insulator broken or hardware may be broken, like the picture which is showing here in the middle left. So also the conductor also may be failure due to overload of the conductor tension or material poor material quality. Also the structure collapse due to the poor material quality in bracing or any members in the overall structural frames. And the fourth one is foundation failure. There may be some differential settlement in in transmission line tower foundation due to the poor soil behavior, so that the differential settlement may happen. So due to that, the entire transmission line tower will tilt, like showing in the picture. And also the unpredicted load such as avalanche, mislanding of a flight, and many uncertain loads. So these loads are to be considered in security requirements or failure containment loads. And the third and final one is a safety requirement. This is related to the construction and maintenance loads, where the stringing loads and the erection loads and even the testing, the proto testing loads also we need to consider in this. Also the man with the kit to be considered here, so that the arms which is a weak while there is a overhanging in that cross arms. So these loads are to be considered in safety requirements. So let me look into detail about these classifications of load. First one is reliability or climatic loads. In this reliability and climatic loads, we need to do a two-way of analysis. One is we need to consider 100% of design wind with everyday temperature. Say for example, in India, in most of the cases we used to have everyday temperature, average temperature range from 25 to 34 degrees Celsius, which is in positive side. So that everyday temperature we need to consider on the conductor loads, conductor tension load calculation, and the 100% design wind also we need to consider in entire structure and to the conductor, string insulators, earth wire, all those components we need to consider this 100% design wind. We know that whenever there is a dip in temperature, there also a dip in wind velocity. So the second case is like 36% of design wind at minimum temperature. Say for example, minimum temperature means it will less than the datum line. Say for example 0, less than the value of 0 degrees Celsius. Say it may be -5 or -20 or -40 degrees Celsius. It depends upon the location of the transmission line tower we need to consider. So these are the two way of analysis. Let me discuss in more detail about this. What are these two way analysis to be done? Why these two analysis required? So considering a tower like showing in that picture in the left hand side, so which are subject to 100% design wind. Also it is connected with the conductors at the three levels, that is lower, middle and top face locations, which are subjected to a wind, 100% wind, which will cause a sway in a horizontal or a transverse side. Also due to the everyday temperature and the self weight of the own conductor, the conductor will deviate or sag, so that the ground clearance may be suffer. So in order to reduce the sag, we need to apply a tension on both the edges of the conductor, like showing in arrow mark. So that static tension we need to calculate by using the climatic parameters and the conductor behaviors such as the diameter, area of cross section, all those things. So suppose while calculating this 100% design wind and at everyday temperature we used to find 1 times the tension value, we need to apply this 1 time tension on the conductor fixing area of all the tower point. Addition to that, we need to consider the 100% design wind for total transmission line components such as tower structures, insulators, earth wire, conductors, and all those components we need to apply this 100% design wind, so that this first way of analysis get completed. And in the second way of analysis also we need to have 36% design wind at minimum temperature. So as we said earlier, as we know that whenever there is a dip in the temperature, there are also a reduction in wind, design wind velocity. So this is a second way of analysis. So the tower and all the transmission line components should be subject to 36% of design wind. And when talking about the conductor tension, static tension, mechanical tension we used to calculate, in that we are going to consider 36% of wind, design wind, so that wind sway, the sway on conductor due to the reduced wind will have less sway. On the other hand, due to this minimum temperature, because of the flexural behavior of aluminum conductor, the conductor get contraction more when compared to the everyday temperature. So suppose that the minimum temperature is -5 degrees Celsius, means the conductor will get more deviate when compared to the everyday temperature 34 degrees Celsius. So in order to minimize the sag, say for example you can see a 3 datum line here. In the bottom level you can see a ground level in a red color dotted line. So in this both cases, both the two way of analysis, the tower is kept in a red color datum line. In the next to that, in the top datum line in blue color, you can see it is a fixing point of conductor. In the left hand side and the right hand side, both the side the fixing point remains same, but the sag peak measurement level, the line in green color you can see. In the left hand side, the sag is touching the datum line marked, because that green line is the reference line for the left hand side sag. In the right hand side, if you see that sag is more when compared to the green color datum line of left hand side sag. So it means ground clearance for right hand side is lesser than the left hand side. So the measurement, if you taken from the left hand side having the 100% design wind at everyday temperature 34 degrees Celsius is more clearance we are having, less sag. In the right hand side, if you see, there is a huge sag which affect the ground clearance. So in order to reduce the sag or in order to increase the ground clearance, we need to apply more tension compared to the left hand side. So for minus 5 degrees Celsius, we need to apply the pull in both the edges with more than 1.5 times the left hand side tension. So adding these two, conductor tension at the fixing point of the transmission line tower plus 36% design wind for whole transmission line components, we need to consider as a second way of analysis under reliability or climatic loads. So here the minus 5 degrees Celsius is considered. So in this case, the conductor tension is more than 1.5 times the left hand side tension for everyday temperature. So in case for Northern European and the North America, in even some part of Russia in the northern direction, the value this minus 5 degree will increase more than, will decrease even less. It will range from minus 40 degree to minus 60 degree Celsius. So in that time, that conductor tension will 4 to 5 times bigger than the left hand side analysis one time tension at everyday temperature. So we need to do the two way of analysis in reliability loads for better design. Next one is security failure and contaminant loads. In this there are two components. One is anti-cascading loads, another one is torsional and longitudinal loads. So this anti-cascading loads, we need to refer class 14 of IS 802. Also this security failure contaminant loads, we need to refer class 11.3. So the class 14 mentioning there is a 3-dimension loads to be applied under this anti-cascading loads. One is transverse loads. In this case, we should not consider any wind loads. We can consider these transverse loads in tension towers and even dead end towers, because for suspension towers there won't be any transverse loads, because the suspension towers don't have any conductor deviation. So due to not having the conductor deviation, there won't be any transverse loads in suspension towers. So this transverse load case is applicable only for the dead end tower and the tension towers. Tension towers with angle, for example, for small angular tension towers, the angle of conductor deviation may be vary from 0 to 5 degree, and for medium it is 5 to 15 degree, and for large it shall be 15 to 30 degree. So likewise there are various type of tension towers under angle. So we need to consider the transverse loads accordingly. Then next one is vertical load, is a summation of weight of conductor in intact span. Intact span is there is no, not considered to be a broken over condition. It should be, we need to consider the full weighted span. And the weight of insulator, string and accessories to be considered under vertical loads. And the third one is the longitudinal loads to be considered based upon the mechanical tension calculated at no wind and everyday temperature. Everyday temperature we had seen in our previous slide with 34 degrees Celsius. So with that 34 degrees Celsius and no wind consideration, we need to calculate the mechanical static tension, and we need to apply those value in one side with 0 degree line deviation. So we should not consider any deviation, even though there is a deviation, conductor deviation in angle tower in the range of 5 to 30 degrees slope. We should not consider those actual conductor deviation. Only we need to consider the 0 degree. That means the conductor is spanning longitudinal direction with its own span. Hence there is no deviation. Even though there is a deviation, we should ignore that deviation, and we need to consider only the longitudinal loads calculated in conductor static tension with considering the everyday temperature and no wind condition. So let me see what is that one side load to be applied. So this is a transmission line configuration having a 3 number of towers located in some span. So there are conductors are connected at various level R, Y, B. For the illustration purpose, we are considering here only single circuit in the conductor terminal, but in case of tower structure, you can see there is a double circuit. You just ignore those. So this is the middle tower we are going to design now. Suppose due to the right hand side conductor sag, there may be a static tension which is in the left hand side the pull. The arrows which are showing in the left hand side is a static tension applied for the conductor in the right hand side. Similarly, for the left hand side conductor sag tensions, we need to apply a pull towards the right hand side, that is showing in a red color arrows. Suppose the value of right hand side tension is 2 times when compared to left hand side conductor 1T into 6. 6 is the number of conductor connected as a double circuit. So we must ignore the least tension values in one side, and we need to apply only the one direction force, that is 2T into 6 we need to apply in the tower. So this is what one side we need to apply as a anti-cascading loads. Other side we should ignore. We should not apply, because if we are applying the both things, the resultant force will only apply on the tower, so that the tower design may be optimized design, but in case of anti-cascading effects, this tower may get failure. So we need to design one side maximum tension on conductors. So this is an anti-cascading loads application. So next one is torsional and longitudinal loads. This is nothing but broken wire conditions. So in this criteria, we are going to assume there will be a one conductor or one wire will get broken due to the material quality, poor material quality. So let me see. So this is a single circuit. In this, the top face of conductor get broken. All the other two face conductors and the earth wire is intact span. Intact means it is not broken. We need to consider total weighted span and the wind span. But in this broken wire at the top, we should consider the broken wire span alone. Similar like the second case, we need to consider the mid face is broken, all the other wires are intact. In the third one, the lower face conductor is broken, all the other wires are intact. And the finally fourth load categories, earth wire is broken, all the conductors are intact span. So these are about the single circuit. When coming to the multi-circuit, for suspension tower, we need to consider similar like this single circuit tower. So considering a one phase failure parallelly, and in case of angle tower and the dead end tower, we need to consider like the last right side picture. We need to consider two phases are failure in one side, all the other conductors and earthware are intact. So similar like for another cases in the right hand side, you can see three phases in one side are failure, all the other spans are to be considered as intact span. So these are the major cases we need to consider for torsional and longitudinal loads. Next is safety and construction. Safety or construction and maintenance loads. So this is imposed on towers during construction and maintenance of transmission lines. Loads due to workmanship with equipment to be considered, and tension loads which are to be applied for testing to be considered. So for you can see there are three pictures. In the left hand side it is a dead end tower, in the middle it is a suspension tower, and in the third right it is a angle tower or tension tower. So for tension, for dead end tower, as per the IS 802 class 11.4, we need to consider normal condition of tension of conductor or ground wire at everyday temperature, but wind load should not be considered. No wind consideration we need to have. So in this case, we need to apply tension of conductor and ground wire to all the fixing point, and at everyday temperature conductor load to be considered. So in the next one, for suspension tower, only the direct value is given under broken wire condition. That is longitudinal loads we need to apply as conductor tension equal to 10 kilonewton, ground wire tension equal to 5 kilonewton. So how many circuit or how many phases, it is not relevant. We need to apply for every conductor fixing point 10 kilonewton, and every ground wire fixing point we need to apply 5 kilonewton. And the third one is line tension tower or angle tower. In this we need to apply a broken wire condition considering the longitudinal loads, which is 2 times the sag tension at everyday temperature. And in this case also we need to consider to avoid wind. So wind load should not be considered in this case. So these are the three major loading parameters we need to have while doing the design of transmission line tower. We will meet in the next video about static tension calculation using the temperature for everyday and minimum temperature, 100% wind, design wind, and 36% design wind, and all the combinations of loads required to calculate sag tension. So we will be seeing in another video. So with this, the loading parameters of transmission line get completed. Thank you for watching. Look at description for more related video. Subscribe to this channel for more updates. Thank you.